Okay. Indeed, universal fault-tolerant quantum computation on decoherence-free subspaces. This is work which was done jointly with Dave Bacon and Julia Kempe in the research group of Professor Breguet Whaley here at UC Berkeley. We heard a lot this morning about the fact that quantum computing must be performed in the presence of errors. And there is no doubt that this is true. However, the pessimistic conclusions that were reached by the previous speakers concerning the thresholds rely on the assumption that the errors have a certain nature, namely that the errors are local or independent, and that they can be written in this form. For example, bit flip acting on qubit number 1 and then nothing on the rest, or a combined bit and phase flip on qubit number 2 and then nothing on the rest. So this is the model of independent or local errors. Now, what I would like to show you today is that if I'm allowed to change the error model, then much nicer results can be obtained in terms of the demands on fault tolerance and the thresholds. In fact, if we're allowed to lower the temperature sufficiently in a physical system, what's going to happen is that we will increase the effective bath wavelength, and as a result, the bath will not be able to distinguish the qubits as well as it would if the temperature is high. Essentially, we're quenching out the high frequency modes of the bath, or the small wavelength modes of the bath. The small wavelength mode is the case where we have these independent errors. But if there is a scenario, which is a question of engineering, I believe, more than anything else, where we can sufficiently lower the temperature, then the bath wavelength will become so long that errors will have to be correlated in the sense that the bath can no longer distinguish the qubits. And this is the case where the errors become correlated, or specifically the model I'll be talking about is when the errors are collective, and I'll define this. In this case, the errors have a different form. Rather than acting independently on each qubit, they act something like this. Say all the qubits undergo a bit flip simultaneously, or all of them undergo a phase flip simultaneously. And in this case, in this very idealized case, where the errors are completely correlated, in fact, there is no question of a threshold anymore. It's eliminated. So this is what I will try to convince you of today. But before that, let's define some basic concepts such as decoherence. So everybody knows that decoherence is the process whereby a system is sitting in a bath, interacting with that bath. This is supposed to be the Hilbert space of the system, and there are operators acting on this Hilbert space as a result of the interaction with the bath. For example, suppose the bath loses a quantum of energy, or it actually loses a particle, or it gains a particle, a quantum of energy, or there is an elastic process whereby there is a scattering between the bath and the system. These processes would be described by the Pauli sigma plus minus and Z matrices. But the idea of a decoherence-free subspace is that it might be possible, under appropriate circumstances, to actually find a little quiet corner in this big Hilbert space. And inside that quiet corner, we are hoping there won't be any decoherence at all. So this is the concept of a decoherence-free subspace. And now I'd like to define it more precisely. Well, we have a system with its Hilbert space, a bath with its own Hilbert space. There are states spanning the Hilbert space of the system, the same for the bath. The overall universe is described by tensor products of system and bath states. And on this universe acts a Hamiltonian, which totally generally can be decomposed into this kind of a sum. There is a term that acts exclusively on the system with identity on the bath, then the opposite identity on the system something on the bath, and then this is the troublesome interaction term, which is the source of all the trouble, of the decoherence in particular. Now, the general dynamics of system plus bath is described by a unitary operator, e to the minus iht, where this is just a combined Hamiltonian. And here is the idea of decoherence-free dynamics, or a decoherence-free subspace. Suppose that somehow we could take this unitary operator and make it act as a tensor product. Something on the system, tensor something on the bath. In general, this can be expected to occur only for a subspace of the full Hilbert space of our system. And if there exists a subspace on which the unitary evolution acts in this form, in a tensor product form, that subspace will be called a decoherence-free subspace. What is this condition equivalent to? Actually, it's equivalent to eliminating this interaction term when we restrict the dynamics to this special subspace. So on the subspace, the interaction Hamiltonian vanishes. That's the condition. If this can be made to hold, the dynamics will be decoherence-free. And in that case, the evolution on this decoherence-free subspace, or DFS, will be unitary. And it will be given by the system unitary operator. Now, why is this a good thing? Let me contrast it with quantum error correction as we heard about this morning. And I apologize for anyone I left out on this list here. Basically, active quantum error correction happens in the following way. There is a state which we encode by some unitary transformation into a new state phi. Then we have these independent errors. They transform our state to a new state, an errored state, omega. This state is now measured and diagnosed. We fix the error. Hopefully, we go back to the encoded state phi. Then we do our quantum computation. Then we do decoding. And this cycle continues. Now, contrast that with the situation when we have a decoherence-free subspace. I apologize for the shameless self-promotion here, but this was part of the slide was part of a job talk, so I'm sure you'll understand. So look at this complicated circuit, and look at this rather simpler-looking circuit. We start with a state psi, encoded now into the decoherence-free subspace. We have a state phi, just like above. Now we have some errors, generally correlated errors, and these errors don't do anything to our state, which is great. We don't have to do any of this active feedback loop thing. We just do our computation, and we just don't care about the errors. At the very end, we decode and get the result. So this certainly looks like an attractive prospect for quantum computing, and I'll try to convince you in following that it's actually possible to do universal fault-tolerant computing in this way. But first, what is the condition in order to actually see or have a decoherence-free subspace? There are many ways to get this condition. I wrote 3 down, and hopefully at least one of them will appeal to each member of the audience, depending on your background. Probably the most intuitive is the Hamiltonian formulation. Here is our interaction Hamiltonian. We can always write it in this form, as a sum of operators acting on the system, tensor something acting on the bath. This is completely general. Now, what is the condition for a decoherence-free subspace? A state will belong to a DFS if and only if the action of the system operators on it is scalar. That's the condition. This must hold for a state to belong to the decoherence-free subspace. All the system operators appearing in the interaction Hamiltonian must act on it as a scalar. This can actually be simplified. Turns out that, as is the case in many physical situations, if these operators form a semi-simple Lie algebra, then it's not just a scalar. In fact, this is 0. So that's one way to state the condition for a DFS. The other way is using the Lindblad master equation. I don't know how many people here are familiar with it, but let me just say very briefly that one can, in the Markovian approximation, one can write down a differential equation describing the dynamics of the density matrix of our system. It contains the usual unitary term, and then there is this new addition due to Lindblad, which describes the decohering dynamics. And the condition under this formulation, which is approximate because it's Markovian, is very similar in appearance to this condition here. Now it's not the S's, but rather these operators, the F's, which are also system operators, which must act as scalars on our states. And finally, in quantum error correction, what is often used is a different representation, namely the Krauss operator sum representation, which was mentioned earlier this morning. This is again exact. The dynamics of the density matrix is now described by a sum over operators like this. The condition on these operators is that the sum of A dagger A is identity. And in this case, again, we get a very similar looking condition. Now it's these Krauss operators that must act as scalars on our states for the states to belong to the DFS. So pick whichever you like. In all cases, the bottom line is that when the condition is satisfied, the dynamics of our system described by its density matrix, which is given by trace of the bath of the full evolution, this dynamics is unitary, and it's governed by the system Hamiltonian alone. So this is just to say that the dynamics is unitary, there's no decoherence. And that will be a result of this condition being satisfied. In fact, it's if and only if. So I'd like to interpret this condition for you for DFS. And there are several interpretations one can give. Formally, considering these S alphas, which appeared in the Hamiltonian, to be a Lie algebra, then this condition for DFS is just the condition that the states I are the singlets of the Lie algebra. In other words, that these states behave as scalars under this Lie algebra. Or in other words, these states transform according to the one-dimensional irreducible representations of the Lie algebra. In the case, by the way, I'm saying Lie algebra, you may wonder whether it's always a Lie algebra. In the case of, in the Hamiltonian formulation, very generally it is a Lie algebra that is satisfied by these operators. In the Lindblad formulation, not always, but in many cases still it is. So this is a pretty general interpretation. A slightly more physical interpretation, and let's specialize to the case, the semi-simple Lie algebra case, where the states that belong to the DFS are annihilated. Now, how do we think of these states? These states, if this is a Lie algebra, they often form or can be thought of as some generalized angular momentum algebra. So we have some angular momentum describing our system. And the states we're looking for are those states that have zero angular momentum under the interaction with the bath. So what does that mean? If they have zero angular momentum, there's some kind of a spherical symmetry, some isotropy going on. And basically the bath cannot distinguish the structure, the internal structure of the states because of this isotropy. That's the meaning. I find that an appealing physical interpretation of the meaning of having zero angular momentum. This is not a real angular momentum, mind you. Of course, it's some kind of effective angular momentum. And finally, perhaps the most useful interpretation is to observe that this condition, or the more general condition with the C alphas, expresses a degeneracy. In other words, we're looking for states that are degenerate with respect to the system operators. If they are degenerate, that means there is some kind of symmetry. So what are we looking for in general? We're looking for a symmetry in the interaction between the system and the bath. That's the guiding principle. Okay, so keeping that in mind, one must impose one important additional condition, which is that while we have taken care of the interaction between the system and the bath causing decoherence, there may still be a contribution due to the system Hamiltonian that may take the states out of the protected subspace. So we must make sure that the system Hamiltonian itself doesn't spoil the situation by taking us outside of the subspace. and that's expressed here. The system Hamiltonian must preserve the DFS. So that's an additional condition we must impose. Now I'd like to give you an example, the most important example that we have. No. The condition that's stated here yes, but this refers to not to the system Hamiltonian, but to the interaction Hamiltonian. So the DFS condition, as I've stated it so far, relates to the interaction Hamiltonian. Now I'm adding an additional condition which relates to the system Hamiltonian. So now I'd like to give you examples of decoherence-free subspaces. In fact, I'll give you just one example, the most important example, the situation that arises under what we call collective decoherence. As I alluded to before, the assumption that errors are independent is what led to the conclusion that the threshold is very small, etc. And we would like to focus on the case where there's a symmetry in the interaction between the system and the bath. And the symmetry that I want to focus on in particular is the situation where there is a permutation invariance in terms of the qubits interacting with the bath. So if I can permute the qubits and the bath wouldn't know, that is the situation of collective decoherence. What is the physical situation in which this would occur? It's the case where, for example, here are the qubits that have some small spacing, and here is the bath described by some long wavelength. Lambda is much greater than delta x. In that case, we would expect the qubits indeed to have a permutation invariance as far as the interaction. With a question?
If the error is permutation independent, is that not significant? You mean that if there's a small region which is being coherence-free, then everything is coherence-free?
No. No, you'll see that that's not true. Another question?
When you allow things such as, well, exactly again, qubits are up again or down, it would that's allowable.
You'll see the actual form of the states, and they're more complicated than that. What this condition means is, again, think of the first slide I had. The errors will act something like XXXX or ZZZZ. So it's really a condition on the errors, not so much on the states right now. You'll see what the states are that arise from postulating this kind of an interaction. To make this formal, it's useful to introduce the so-called spin boson model. And the spin boson model is just a simple model that describes an interaction, a general interaction between a system and a bath. Assume that there are two types of processes. A process whereby this blue is the qubits, so they lose a quantum. Bath gains a quantum, so sigma I minus bk dagger. In this case, this is a notation for phonons. So I'm assuming that there's a down transition in the system, and then there's concurrently there's a phonon with mode with wave vector k that's excited. Of course, the opposite process could also happen. That's described here. So sigma I plus bk. This is create a system, quantum, annihilate a phonon, and this is the opposite. And then there could also be a conservative, energy-conserving process due to dephasing, and that would be described by sigma iz acting on the qubit. This is I, of course, is the qubit index tensor with this kind of a form for the bath. So let's assume that we have this kind of an interaction Hamiltonian. It's a very useful and widely studied interaction Hamiltonian, this spin boson model. And it's important to note that these operators here, the sigma I plus, sigma I minus, and sigma iz, they satisfy a local SU2 algebra. Okay, now I'd like to make the collective interaction approximation. So I'd like to make the assumption that indeed we have this long wavelength and the qubits are commutable. In that case, I can simplify this Hamiltonian drastically. And the way to do it is by saying that these parameters here, the g, I, k, expressing the coupling between the bath mode k and the qubit I, that they don't depend on the qubit index I. if you make this assumption, then immediately you get particle permutation invariance. And you can drastically simplify this Hamiltonian in the following way. You define collective operators, just summing over all the qubits, and rewrite the Hamiltonian in terms of these new collective operators. And of course, you get just 3 terms corresponding to the plus action, minus action, and the z action. So now we have instead of 3n, we have just 3 operators. And this is the algebra that describes the interaction between the system and the bath. This, once again, is an SU2 algebra. Just like this local SU2, this is a global SU2 algebra. We can use these 3 operators, or the fact that it's an SU2, to find the states that are decoherence-free. I'm sorry? Put it over there? Okay. So how do we find the states? Recall the condition. We have to find states that are annihilated by our system operators. Well, it's actually a pretty elementary exercise in angular momentum theory to find states that have total 0 angular momentum. That's what we need here. So suppose we have just 2 qubits. Then you can easily convince yourself that this state, this one singlet state, has 0 angular momentum. So this is the decoherence-free subspace when we have 2 qubits under collective decoherence. From the point of quantum computation, that's not very useful because it's just one state, and obviously we need 2 orthogonal states to encode a bit. So we have to go to 4 to see the first interesting case. In order to explain to you what these states are for 4, I need to introduce the other 3 states that you get for 2 qubits. 2 qubits will span a 4-dimensional Hilbert space. This is just one of them. And then there is a triplet. And you can write down states, again, using elementary angular momentum arguments, which once again have 0 total angular momentum. J is 0 in both cases. And they will be a product of the 2 singlet states on qubits 1 and 2 and qubits 3 and 4. That's easy. And then there's a more complicated state here. And I've written out explicitly what they look like in terms of 1s and 0s here. So this state is decoherence-free. This state is also decoherence-free under this interaction, the collective interaction. Now we have 2 orthogonal states, and we can use them as a full encoded qubit. In particular, we can write out superpositions such as A0 logical plus B1 logical, where this is 0 logical, this is 1 logical, et cetera, et cetera. It goes on for larger numbers of physical qubits. How do we actually find the general recipe? Here's a nice diagrammatic way to see it, at least to count the number of states. So here's how it works. The horizontal axis is the number of physical qubits in the system. The vertical axis is the total angular momentum. You start out with having 1 spin 1/2 particle. Then you add another spin 1/2 particle. Then the rules of adding angular momentum tell us that we can add angular momentum in 2 ways. We can either add a half or subtract a half. This path is the upper singlet state here. This is 2 physical qubits having total 0 angular momentum. Okay, so we get just 1. Now suppose we want to go to 4 particles. Then we have to count all the paths that lead us to here. Again, having total 0 angular momentum. There are 2 ways to get there, this way and this way. So we have 2 states. That explains why I have only 2 states here. You keep on going. For 6 particles, you count 5 different paths ending up at 0 total angular momentum. For 8, you get 14, etc. And this is the general formula. So what this expresses is that as we increase the number of physical qubits, under the assumption that collective decoherence remains the dominant interaction between system and bath, we can encode 1 state, 2 states, etc. In general, this many states. Log to the base 2 of this will tell you the number of encoded qubits in the system. Now, there's a very interesting result here. If you actually take log base 2 of this, this is asymptotically what you get. It's n minus a logarithmic correction. This is, as I said, the number of encoded qubits. Divide that by n, which is the number of physical qubits, and it goes to 1 asymptotically with only logarithmic correction. What that means is that this code has unit efficiency. So as a code, it fills up the coding space. That's an important property that I'll want to use later on. So I want to summarize up to this point. What I've shown you is what the condition for decoherence-free subspace is. And I've given you a physical example, namely the situation of collective decoherence, where one would actually observe collective decoherence. And I've shown you how to obtain the states and count them. But now the question is, all right, I have this decoherence-free subspace. How do I compute on it? So that's the question of universal fault-tolerant computation on a DFS. Now, let me address first the issue of fault tolerance. Suppose I showed you how to do universal computation on a DFS. That is, staying entirely inside the DFS all the time. If you're staying inside all the time, the errors don't touch you. So there is no question of fault tolerance here, because it's automatically decoherence-free. The only question of fault tolerance arises when there are perturbations that take you outside of the subspace, because the error model was overly simplified. But within the idea that collective decoherence is really what's going on, there is no question of fault tolerance, because everything we do is automatically decoherence-free. So now it remains to show how one can actually implement universal computation. And for this, we recently developed a stabilizer formalism. I see that I'm very short on time, so let me just give you the bottom line here. Yeah, 5 minutes, okay. One can define a stabilizer. I've written it out here in terms of the interaction Hamiltonian. This is what the stabilizer will look like. The stabilizer, if you remember, is an operator which fixes the states, in this case, the states of the DFS. This is a very different stabilizer from the one we saw this morning because it's non-abelian in general. Now, you can use this stabilizer in order to derive a condition such that Hamiltonians do not take you outside of the subspace, outside of the DFS. And if you go through a little bit of algebra, you find that such a Hamiltonian it is sufficient for such a Hamiltonian to satisfy this condition. The Hamiltonian acting on the stabilizer essentially commutes with the stabilizer, except that these parameters V here, which appear here, these are some angles, they may change. And they have to change in a one-to-one fashion under this commutation operation. So this is the condition. And in fact, I'll just need the simplest version of it, which is the condition is Hamiltonian commutes with the stabilizer. That's all we'll need, at least for collective decoherence. So if the Hamiltonian commutes with the stabilizer of the DFS, then such a Hamiltonian will preserve the DFS. So we can use Hamiltonians of that type in order to perform calculations that keep us always inside the DFS, thereby, again, avoiding the question of a threshold for fault tolerance. So what are the relevant Hamiltonians for collective decoherence? Again, in the interest of time, let me skip some details and let me assume that we're in the collective decoherence scenario. We can now work out explicitly what the stabilizer looks like by just plugging in these operators. And what you get is very easy to see, actually, is just identical rotations. G sub j is a rotation on qubit number j, identical rotations on all the qubits. That's what the stabilizer looks like. So the collective decoherence errors are just identical rotations in all the qubits. Unsurprising. And now, if this is the stabilizer, and we have to find a Hamiltonian that commutes with this stabilizer, then you can see right away that anything that will just permute two of these rotations, since the rotations are identical on different qubits, anything that permutes these rotations is a valid action. So what is the relevant class of Hamiltonians? It's exchange, which I'll denote by E sub ij. And the matrix looks like this. It's 1 and then 0, 1, 1, 0, 1. That commutes with this stabilizer. Therefore, it will always preserve the DFS. So the conclusion is, if we have a Hamiltonian which is a sum over exchange terms, that's a valid Hamiltonian in the sense that it allows to perform operations which precisely preserve the DFS at all times. So now the question is, can we use exchange Hamiltonians to generate SUN, where n is the dimension of the DFS? And the answer to that is yes. Before I tell you about that, I just want to mention very briefly that there are many physically relevant examples of systems that are governed by exchange Hamiltonians. In fact, any system that's governed by a so-called Heisenberg Hamiltonian, where this is total angular momentum of spin I dot total angular momentum of spin j, this is just an exchange Hamiltonian. This is just a sum over exchanges by this simple identity. And one very interesting physical system that was proposed recently, which is governed by this kind of Hamiltonian, is the spin-spin coupled quantum dots by DiVincenzo and Loss. So there's an important physical example here. Now, to the issue of how to implement universal quantum computation on systems that are governed by an exchange Hamiltonian. So suppose we have a system like that, and suppose collective decoherence is what's going on, so we're in the relevant regime. Then we actually worked out recently how to implement universal computation. And this is what it looks like. If you want to implement a sigma z on the 4-qubit DFS, all you need is exchanging qubits 1 and 2. That implements sigma z as a Hamiltonian now. If you want to implement sigma x, it's this linear combination. What that means is that you need to be able to tune the coefficients that sit in front of these exchange operators. And if you can do that, you can form this linear combination, you get sigma x. If you have sigma x and sigma z, you can generate all of SU2. So this is how you generate SU2 on the DFS of 4 qubits. Now let me not go through this. This is just to show you that you can also do controlled phases between 2 blocks of 4. It's a much more complicated construction. The very interesting result that was recently derived, and this is almost my last slide, is that exchange actually acts as an asymptotically universal Hamiltonian for quantum computation. What do I mean by that? Well, I just argued that for 4 qubits, I take all the exchange operators, and I can generate encoded SU2 on the DFS. Now, what about general K? K here denotes a number of qubits. Well, in a paper that will appear shortly, we're showing that, in fact, this set of operators generates the entire encoded SUN on the subspace, where n is the dimension of the DFS. And what this means is that universal quantum computation is possible on any singlet space, any DFS, using just these 2-body exchange Hamiltonians. And if you're familiar with the results about universal quantum computation, that should come as a bit of a shock, because you need the single body operations as well, in general, for universal computation. But here we're claiming that just exchanges, just a single 2-body is sufficient to do universal computation, although in an asymptotic sense. It's asymptotic because, as I said before, the code efficiency here approaches 1 with a logarithmic correction. So to conclude, let me simply pose a list of open questions. I told you that exchange is a Hamiltonian which is asymptotically universal. It's interesting to speculate what the other sets of 2-body Hamiltonians are that are asymptotically universal in the same sense. And we conjecture, in fact, that, or I should say I conjecture, I haven't confirmed this with Julia, that it's all of them, but for a set of measure 0. One clear subset which is not going to work is Hamiltonians which are decomposable into tensor products. And the other interesting question is, since we have this asymptotic result, can the efficiency be improved? By using a different set of Hamiltonians, can we get a better efficiency than this log k over k correction? Thank you for your attention.